So in this problem, we're given that a rocket ship of mass m is being pulled to the right by some force F equals alpha t squared. It's actually being propelled by its own rocket engine, and we're going to ignore the fact that in order to do that, it is shooting some mass out behind it. We're going to ignore that change in mass and assume that it's negligible. So what we're going to do is we're going to use Newton's law, F equals ma, and apply that to this situation. So then we get m times a equals alpha times t squared. And all we're going to do is pull this mass over to this side to get a equals alpha over m times t squared. And remember that a is just acceleration, which is the rate of change of velocity dv dt. And so now what we can do is take the integral of dv dt from time 0 to time t, and that's going to be equal to the integral from 0 to t of alpha over m times t squared dt. Now, when we integrate this, we're going to get v at some time t minus v naught, the initial velocity, which we're given. And that's going to be equal to alpha over 3m times t cubed, evaluated from 0 to t, which is just going to be alpha over 3m times t cubed. So this, once we pull this v over, is going to be v equals v naught plus alpha over 3m times t cubed. And this is going to be our answer for part A, the velocity of the ship at any time t. Now we're also asked in part B to find the position. And we're again given that the initial position is x naught. So here we're going to remember that v equals dx dt, the rate of change in position, equals v naught plus alpha over 3m times t cubed. And we're again going to integrate from 0 to t of dx dt equals the integral from 0 to t of v naught plus alpha over 3m t cubed dt. Now sometimes students look at this initial condition v naught and say, oh look, it's a velocity, that means it's a rate of change of position, that means I have to integrate it the same way I integrate the velocity on this side. And although that's a reasonable mistake to make, remember that v naught is a constant. The initial velocity is never going to change as time changes, which means that when we integrate it, we just multiply by t. We don't do any other integration rules. So what we're going to get here is the position at any time t minus x naught, the initial position, equals v naught times t plus alpha over 12m times t to the fourth. Now pulling this over, we get x equals x naught plus v naught times t plus alpha over 12m times t to the fourth. And this is our answer for part B for what the initial, for what the position is at any time t.